Okay, so we're now ready to think about hanging something from a wire. And so here's what we're going to do. We're going to take a copper wire, and it's 2 meters long. And just for the sake of simplicity, it's going to be a wire with a square cross-sectional area. What does cross-sectional area mean? It means when you slice through something and then you look at the area of the cut, it's the shape of that. So this meter stick has a rectangular cross-sectional area, but the marker, if we slice through it, would have a circular cross-sectional area. So we're going to make the wire have a square cross-sectional area, so it's going to be a square wire. If you looked end on, it would be square. And so square cross-section. And when we hang 10 kilograms on the end of it, so if we hang 10 kilograms, we get a stretch of 1.51 millimeters. So that would really happen. Okay? And we'll say that the cross-sectional area of the wire, the area here is, we'll say it's a millimeter on each side. So the area is 1 times 10 to the minus 3 meters squared is the cross-sectional area. Okay. So now what we have to do, we can figure out the spring. We can consider this wire as a big gigantic spring, and we could figure out its spring stiffness. And then what we have to do is figure out how many chemical bonds there are along the length of the wire, like how many springs in series we have, and then how many of those chains there are, how many in parallel, and then we can get the stiffness of the whole thing. So what we're going to do is basically, we're going to think about it this way. If we're looking up at the bottom of the wire, we're going to count the number of springs from the bottom of the wire to the top number of bonds, and then we're going to look at the bottom and count the number in parallel, and then we can actually figure out the stiffness of one interatomic string. Okay, so that's not so hard. We can do that. So, first of all, the number of parallel chains. So well, if we looked at the bottom of the wire and we just counted the number of atoms that we saw, that would give us the number of parallel chains, right? So we take the wire, we look at the bottom, and we say, so we just count number of atoms that fill up the cross-sectional area of the wire, and then we've got the number of parallel chains going up. So the area of the wire, so this would be the cross-sectional area of the wire divided by the cross-sectional area of one atom would give us the number of chains. Okay, we know the cross-sectional area of the wire, that is 1 times 10 to the negative 6th meters squared. And the cross-sectional area of an atom for our purposes is the atom is going to be square here. So that's 2.28 times 10 to the negative 10th meters squared. And one atom. Sorry, it says one atom. Cross-sectional area of one atom. So we're looking at that, right? And so that comes out to kind of a big number. It's 1 point something, 1.92 times 10 to the 13th. So that's the number of parallel chains we've got. So the whole wire is 1.92 times 10 to the 13th times stiffer than one chain would be. And now we need to know how many atoms in one chain, number of bonds, number of springs in one chain. Well, that's just going to be the length of the wire divided by the length of one of these bonds, which is the diameter of an atom. So we've got 2 meters divided by 2.28 times 10 to the negative 10th meters. And so that's going to come out to 8.77 times 10 to the 9th number of bonds in one chain. So now we have to let's think about the stiffness of the whole wire. So the wire, when it was supporting a mass of 10 kilograms, it stretched 1.5 times 10 to the 1.5 millimeters. So here's the mass, the gravitational force, the magnitude was 10 kilograms times 9.8 newtons per kilogram. So 980 newtons, right? And that was equal and opposite to F spring. That would had to be 980 newtons. And that was equal to the spring stiffness times the stretch, which we know is 1.51 times 10 to the negative third meters. And so what was the stiffness? The whole wire. Spring stiffness turned out to be, we solve this, divide 980 by that, and it turns out to be 6.49 times 10 to the 4th newtons per meter. And that's a really big number, but it's not very surprising because wires are really stiff, right? A copper wire is actually a stiff thing. So now we want to disentangle this. So we have the following thing. We have the, 998, yes, thank you, 98, right, but that's, I think, still the right number, actually. Thank you. It's always good to have somebody check these. Well, the force, so it's what we did earlier. When the momentum of the block isn't changing, the gravitational force down is exactly equal to and opposite direction of the spring force up. So we know that. We calculate that. We say, well, the spring force has to be the same. That has to be the same. And we know that the spring force, the magnitude of the spring force is the spring stiffness times the stretch, and we know the stretch because we measured it. We're talking about magnitudes here, yes. But so when I write, a standard thing is if you write a quantity that's a vector without the little arrow, it's actually so if I wrote that, it's equivalent to writing that. Now, it may not be a good idea for us to be doing that right now because some of us are still not real good at remembering to put arrows when we are talking about vectors, but magnitudes, okay? Yes. So now we can say that the spring stiffness of the whole wire is going to be equal to what? Well, it's the spring stiffness of one interatomic bond, and then it got stiffer the more chains we had. So we're going to multiply by the number of parallel chains. But it got less stiff the more springs there were in the, so number of bonds in a chain. And so we know this. We just figured it out. We figured that out. We figured that out. This is our unknown. We're solving for this. So let's solve for it. The spring stiffness, we usually use K sub S sub I. That means for interatomic bond. Okay, so this is the this is a macroscopic quantity. It's the whole wire. This is the microscopic quantity we're figuring out from our macroscopic measurements. So this is the interatomic bond, and that's going to be equal to the spring stiffness of the whole wire times the number of bonds in the chain, which was 8. So let's write these numbers. This is going to be 6.49 times 10 to the 4th newtons per meter. That was the whole wire. And this number here, number of bonds in a chain, that was 8.77 times 10 to the 9th springs in a line. And the number of parallel chains, that was 1.92 times 10 to the 13th. So 9 and 4 is 13. That's 13. So it's going to come out to some kind of ordinary number. And in fact, when we work it all out, it comes out to 27 newtons per meter. Kind of a ordinary number. So that's the stiffness of one of these little teeny interatomic bonds in copper. It takes, now you can't apply it, you can't stretch it a meter because the bond itself is only 10 to the minus 10th meters long, but so let's write this. So this is so let's just recap what we did here. We figured out how stiff the whole wire was, considering it was a big macroscopic spring. Then we figured out how many parallel chains there were, because that told us how much stiffer it was than an interatomic bond. And then we figured out how many bonds there were in a chain, because that told us how much less stiff it would be, and then we were actually able to get the interatomic spring stiffness, which is actually a moderately cool thing. Now, it turns out that there's a macroscopic measurement that you may run into, that people in a lot of different fields run into all the time. It's called Young's modulus, and it's the relationship of, and you'll see it tabulated for various materials. So if you're in material science or civil engineering or mechanical engineering or geology or lots of things, you'll see Young's modulus. And what that is it's the ratio of the force, tension force in the wire to the cross-sectional area of the wire. This is called stress. And then this is the fractional stretch. So the amount the wire stretches over its length, that's called strain. And if we go through the math, which we'll do next time, it actually ends up that we can show that if we know Young's modulus from making these measurements, we can actually, it actually turns out to be equal to this interatomic spring stiffness divided by the length of one of these bonds. So we can actually figure these things out directly from these macroscopic Young's modulus measurements.